Think of standing alone in a vast, open field at midnight. The air is perfectly still. The silence is so complete, you can almost hear your own heartbeat. Then, without warning, a deep rumble vibrates through the soles of your shoes. People everywhere report these sudden, unexplained booms. Depending on where you are standing, it might sound like a distant artillery explosion, or a low clap of thunder echoing from directly underneath the soil. These aren't isolated tricks of the mind. Thousands of widespread reports confirm physical events are happening beneath us, leaving scientists to track down exactly what is generating the noise. The quiet we think we experience is an illusion. We walk on a surface that feels like a solid, static shell, but the reality is entirely different. The Earth's crust is divided into massive tectonic plates, locked in a continuous cycle of colliding and pulling apart. At these boundaries, extreme heat and pressure accumulate directly at friction points. When the rock snaps, stored energy releases instantly, generating powerful kinetic waves that propagate outward. When we hear an inexplicable boom in a seemingly quiet landscape, our senses are often just intercepting that escaping kinetic energy. The planet is in constant motion, and we are physically feeling the result. To find the source of these noises, researchers look first to the most massive generators of kinetic energy. Earthquakes emit specific low-frequency seismic waves. Because of their length, these waves can travel vast distances straight through the Earth's dense interior. These frequencies are often too low for human ears to detect as distinct audio. Instead, we physically feel them as a vibration in the ground, before the brain can even attempt to process them as a sound. Volcanic regions act as a second, continuous engine for deep geological rumbles. Deep below a volcano, fluid magma and heavy volcanic gases are constantly shifting inside confined chambers. This diagram illustrates a subterranean magma chamber. As pressure fluctuates, expanding gas bubbles force the surrounding rock strata to fracture, forcefully releasing gases. Long before magma ever breaches the surface, specialized seismometers detect the distinct low-frequency acoustic signature of this underground movement. If you happen to be standing a few miles away, this invisible pre-eruption activity simply sounds like the Earth is groaning beneath your feet. Together, grinding tectonic plates and circulating magma create a massive baseline of subterranean noise. The Earth's crust effectively acts as a giant acoustic amplifier for the forces shifting below it. But the source of an underground rumble is not always underground. Often, the vibration originates high in the atmosphere or far out at sea. This introduces the concept of infrasound, massive sound waves that operate entirely below the 20 Hz limit of normal human hearing. Here we see enormous natural events, like severe offshore storms, generate wide infrasonic waveforms. These waves travel thousands of miles through the atmosphere without dissipating. When they collide with a landmass, the acoustic energy transfers directly into the soil. You feel a ground vibration, though the source is above. The ocean acts similarly. When a heavy swell slams against a steep underwater cliff face, it sends low-frequency shockwaves through the seabed that can be felt miles inland, easily mimicking a minor earthquake. Then there is human industry. Deep mining operations, heavy construction, and industrial traffic produce rhythmic ground vibrations that are indistinguishable from natural geological forces to the untrained ear. Investigating a mysterious boom means mapping these variables. You have to rule out distant storms, ocean swells, and nearby factories before you can conclude the sound is truly coming from deep inside the Earth. When scientific instruments intercept a new, unexplained ground vibration, researchers apply a strict process of elimination. The first step is isolating the exact timing and location of the acoustic signal, then cross-referencing it with existing global databases. This split-screen chart shows the methodology in action. The system checks the raw audio waveform on the top against known barometric pressure changes, local industrial blast schedules, and seismic records below, looking for a precise matching peak. The approach is entirely data-driven. The investigators aren't looking for a supernatural explanation. They are searching for the specific, known physical mechanism that generated the pressure wave. Yet, even after this rigorous filtering, some recorded signals simply do not match any known geological or atmospheric event on file. An unresolved signal isn't evidence of magic, it is a mathematical gap. It proves our instruments are sensitive enough to capture a physical process that we simply haven't gathered enough data to identify yet. What these recordings ultimately reveal is that the Earth is a highly dynamic, noisy system. Rocks are continually fracturing under pressure. Glacial ice sheets grind against bedrock. Atmospheric pressure zones collide and collapse. Every one of these actions generates kinetic energy. Our biology restricts what we can hear. We walk across a planet that is constantly communicating through physical vibrations, and human ears capture only a tiny, localized fraction of that global activity. The next time you feel a sudden vibration in the ground, remember that the planet is speaking. The real work is figuring out how to listen and translating the physical language moving beneath our feet.